The floor is yours.
Thank you.
Take it away.
Yeah, so as the operative word is dabbled, because so I'm not an expert in R or meta-analysis, but I have used it, so I'm like, I can impart knowledge on how to consume this software rather than kind of all the background statistics and stuff, which I'm not, I'm not great on. So that's my disclaimer. I'm just showing you some stuff that I've used and I've got it to work. There's probably alternative ways of doing these things, and if anyone has like questions and suggestions as we go along, please chip in. Obviously, I think there's a very mixed kind of knowledge level of kind of R and meta-analysis in the room, I believe. So if I'm pitching it wrongly, if you don't understand something, please let me know. So in terms of a plan for the talk, there's kind of like the theory side of things, and then there's the how-to side of things, and I'm going to flip back and forth between them. So in the theory side, kind of what's meta-analysis, where are we starting from, how to organise what's going into it, some stuff about converting between effect sizes, and more technical stuff. And then on the how-to side, it's actually like how to tell R to do what you want it to do. So what is meta-analysis? Or what is meta-analysis? It's a set of statistical methods for pooling results from different research studies that have investigated similar things. And when you're pooling things like effect sizes, you need to make sure that they're compatible with each other so that they're on the same scale. And I'll talk about that. And with meta-analysis, you're aiming to obtain a pooled effect size that is gives more weight to kind of larger studies with less variance, higher precision. So that tends to be studies which have larger samples that get given more weight. In meta-analysis, you can also test for association between variation in aspects of methodology across studies and variation in the effect sizes from those studies. So you can kind of try to look at which methodological differences might be affecting whether effect sizes are larger or smaller. And you can also investigate potential for publication bias. So before embarking on a meta-analysis, you should be familiar with how to conduct a systematic review. So does that make sense to people? Yeah. So you don't want to be doing meta-analysis on very, very few studies. You need to kind of have knowledge of how to do a systematic review, and for it to be appropriate to do a meta-analysis. You should try to pre-register your analytic protocol. In meta-analysis, there's lots of like options on how to do it, so you don't want to be kind of picking and choosing as you go and seeing which one comes out as favourable and which doesn't. You want to plan ahead, and if possible, pre-register your protocol with something like Prospero. And so I'm going to assume that we're at the stage in a systematic review where you've screened your studies using appropriate inclusion and exclusion criteria, and that eligible studies have been selected. And I'll also assume that the relevant data that was provided by those studies has been extracted as best you can according to your protocol. So things like sample sizes and the summary statistics from those studies have been entered into your kind of characteristics table. So then on the R side of things, who has used R before? Most of you? So you probably know all this, but you can download R, it's free, open source. You can get it from the King's Software Centre as well. And also, so R has a bunch of packages that you can install to extend its functionality. So it's got certain advantages against kind of tailored software for meta-analysis. It's free. It's very flexible, so you can kind of customize how to run your meta-analysis. It's fairly simple to use once you know the basics, and it also supports reproducibility because you can share the script that you use to run your meta-analysis. So when you open R, I use R, like basic R. I don't use R Studio. I'm sure it's very good, but I've never used it. I don't know what people's thoughts are on that.
More mental.
This is more like that I've just never had the opportunity, or like I've never learned to use it. So this is what I've learned. So you'll probably have loads of ideas about how to make this easier. So you've got the R console, and you've got your script up the top here. I normally tile my windows horizontally. And so up the top, you can open your script. You can use point and click to install packages if you want to. You can run your code. I won't spend too long on this. So I normally set my working directory when I use R. So it just tells R which folder you saved your data in, so you can just go straight to it rather than having to tell it each time where that directory is. Again, you know all this, but you can use hashtag to comment in R. Does that, for people who haven't used R, does that make sense? So when you're writing an R script, if you put a hashtag at the beginning, R ignores that. It sees it as a comment rather than a direction. So the package that I've used is Metafor by this person, Vish Bauer. You can download it from here. Bug reports are here. I can share the slides, by the way, if you want. So Metafor has a user guide, which is kind of like will tell you everything that I'm going to tell you, but just in a really boring way. So basically, I'm going to try and just pull out some useful bits from this and show them to you. So the way I've envisaged this talk is that I've got kind of screenshots of bits, important bits. If you want me to, I can actually pull up R and show you the running of it, or I can just go through the talk. Does anyone have a preference?
Go for the talk and then
yeah. If there's bits that yeah. Cool. Okay. So when you install a package in R, it will ask you to set a CRAN mirror. Do you all know what this is? If you don't, it is basically where R finds the package from, and you should choose the one that's geographically nearest, I think. And so if I go back to here, if you can like type in to tell R to install stuff, or you can go to packages up the top, and there's a point and click thing for setting the CRAN mirror and installing the package that you want. Yeah. And then you need to tell R to load that package. So this is the command that I use. I think there's others that you can use that do the same thing. Okay, and then you need to ask R to read in your data. You can read data into R from various data file sources. So you can use Excel, SPSS. I think the easiest one is a CSV file, but that's not so easy for so the way I see it, you might disagree, but you've got your data that you've kind of input into a file. I would find it hard to write my data into a CSV file. Do you guys agree? Or, yeah. So I know that people hate SPSS, but I do actually use SPSS to compile my data sometimes. Or you can use Excel. It just lays it out nicely. You can name your variables and all that kind of stuff. But then to do all the kind of complicated stuff, then you want to be using something like R. So I've written in some commands for getting the data. To get an Excel file, I actually only found this out recently. You can copy a whole Excel table and read it into R by typing in this, and it gets it straight from your clipboard. Did you guys know that before? Yeah, I didn't, but you have to actually type that in manually, because otherwise it just copies this. I can show you if you want. Do you want to see? Yeah? Yeah? Okay.
Where's that picture?
Oh, it's in the south of France.
Nice.
It's very nice.
Can't we just look at that instead?
Yeah, that would be great. Did that open? Yeah.
This is being introduced automatically. You can learn
Won't have time to go.
Oh, it's actually opened R Studio. I didn't want that. Much as you guys like it. So if I opened Excel as well, actually I've got an example. So if this is my meta-analysis data, and I'll just zoom into it. I can Control C, and then in R I write oops, that's the wrong one. Didn't like that.
You want to delete the...
Yeah.
Escape.
Oh God. Let me open my script. It's clunky because you have to actually type it in rather than copying and pasting it, because you want it to get what you've copied from Excel. So it has written the data. I don't suggest you use that way. Okay, so there's various ways of doing it. You can get the code from here. When I've done it, I've used SPSS. So this is kind of what I'll show you mainly. So when you read data into R, you need to label it as something. So this is the DAT thing here. I've called my data DAT. You can call it anything you want. And this is the file that I've previously produced and saved. And so R knows where to get it from because we specified a working directory earlier. So it's saying this data file is from here, and there's various options. I use these defaults. So, okay, so the input, your data file, I wasn't sure which way around to talk about this. You need to tell R kind of a basic file for data for a meta-analysis. You've got a column that identifies your studies, you've got a kind of sample size column, and you've got an effect size column. That's kind of the most basic one that you could have. But the problem is that studies investigating kind of similar things often have variable design and analytical approaches, and therefore you're going to have a range of summary statistics that they've given you. But to run the meta-analysis, you need them all to be on the same scale, them all to be compatible. So Metafor has a command that can help you with this. So for example, studies investigating, I don't know why you do this study, but whether ADHD is related to ASD might have investigated it by having a binary variables where you've got how many people who have ASD have ADHD or not, and how many people who don't have ASD have ADHD and not. So that's like you've got two binary variables there. Or different studies might have looked at hyperactivity scores for those with and without ASD. So you've got kind of continuous variable and a binary variable. Or you might have a correlation between hyperactivity scores and social communication scores. So that study's got kind of correlation statistics. So all of those studies might be investigating relationship between ADHD and ASD, but they've all done it in a different way, and they're going to give you different summary statistics. So in order to kind of run a meta-analysis on that, you would need to convert these summary statistics into something that's compatible. So yes, Metafor has this function called escalc, effect size calc, for calculating effect sizes to ensure compatibility. So I've used escalc for a meta-analysis that I did run on correlation coefficients. And that wasn't necessarily to convert, to get information from different studies to be compatible, but it was to because in meta-analysis it's recommended not to use R values for entering into the meta-analysis. You're supposed to transform them to Z scores. So you can use escalc to do that as well. So basically this function escalc, I've laid it out in this table. This is, so in the Metafor guide, it puts all this like in order, but I've tried to lay it out in a kind of more easy to understand way. So you've got the different like types of study. So you might have like a group comparison, or associations between variables, or like a single group to look at prevalence. If you're doing group comparisons, the data that you've actually extracted from the different studies, it might be in the form of like dichotomous variables. So if you're comparing, like the example I used earlier of ADHD and ASD, like rates in each, it might use dichotomous variables, or you might have quantitative variables involved as well. Basically, you've got an input format. So, for example, with quantitative variables, if you're doing a group comparison, you'll have what the study you might have extracted from the study is like the mean and standard deviation of scores in cases and in controls. That's kind of a typical thing that they might have reported. And you can, from this, ask escalc to give you like a standardized mean difference. If you've got the case where it's used dichotomous variables in the original study, you can have an input format where you've got like the frequency of participants who are exposed and unexposed in each of case and control, and you can ask it to spit out a log odds ratio, and you can also ask it to convert that to a standardized mean difference as well. Just to show you this, so with the correlation coefficients, the command to do this R to Z transformation, so this is your data. You are basically overwriting that label. You gave that label to your original data. You're performing a function on it. This is escalc, and now you're telling escalc exactly what you want it to do. So you've got this measure option, tells you which transformation you're requiring. So Z-core is the R to Z transformation. You'll need a column in your data. So this is your like original data up here. The name of your effect size column. So you're saying that is that, and then the sample size, you'll need to give it that as well, and that's the data that you're performing it on. If you run this command, what it will do is it appends these last two columns to your data. So if you had your R column here, it's transformed that to Z. So that's the YI is the effect size column, and the VI is the associated variance. And you can also do a similar thing. I don't think I'll go into this. I don't know, do you want me to? So this is the same thing, but producing like the odds ratio from frequency counts. Do you want to see that? Yeah? Okay. So say this is the data that you have. You've got study 1 and study 2. You've got the number of cases who've had exposure 1. So say you've got the number of participants with ASD who do meet criteria for ADHD. Then you've got the number of cases of ASD who don't meet criteria for ADHD. Oh god, these are bad examples. And then you've got the opposite one. So it's kind of from, you can imagine a table like this. So you've got patients, controls, outcome or exposure 1, outcome or exposure 2. That's a kind of typical table in kind of like a chi-square or something. Yeah. So you want to tell R. So this is that R thinks that this box is called AI, and you want to tell it where to find AI. So you tell it to look in this column of your data. And the same with BI, which is that box, and then CI and DI. So you tell it all that. Again, using the escalc, you want it to give you the OR, or if you want the standardized mean difference, you can use a thing called OR2 SD or something. It's all in the guide. You can look more closely at it. But that's essentially, if you do that, again, it will append onto the end a YI and a VI column, so that's the effect size and the associated variance for each study. Does that make sense to you? Yeah. Okay. And the same thing with the mean and SD. If that's what the study has given you, then again you can imagine it laid out as this. So say you've got ASD and no ASD, you've got a mean score on something, you've got an SD for that mean, and then you've got the number of participants. You might lay it out like this. So study 1, study 2, you've got the number in group 1, the number in group 2, the mean in group 1, the mean in group 2, the SD in group 1, the SD in group 2. And then if you tell it where to find all that information, it will spit out the effect size that you want at the end using its YI and VI columns. So yeah, you'll end up with YI and VI at the end. However you get there, you need those columns in order to run the meta-analysis. I just missed out. You can also use other tools to convert between effect sizes. So I've just put some up here that you can find online, and you can manually produce those YI and VI columns. Yep.
So do you, does that mean you have to have a separate table for each type of study?
Right.
So if you've got a mixture of, if some people have used a binary variable and some have used continuous, you would need separate tables?
No, you don't have to. But you might end up with quite a few columns going on. So I can show you an example.
Ah, okay, yes. So if it's blank in the columns for the other things, then it will merge to the same YI and VI.
Yes. Well, it doesn't necessarily do it automatically. I've just realised my example is in SPSS, so it might take ages to load, and I don't even know if I have SPSS on the laptop. But if you can imagine, you'll have say the study that's given you like binary cell frequencies. You've got your AI, BI, CI, DI, and then you've got another study that's given you means and standard deviations. You'll also have those columns on the end, and they'll just be blank in the different. Now, this is where so in order to eventually end up with a single column of YI, say in like a standardized mean difference, I kind of did my own little workaround to get that all in one, but then, which I can share with you. There might be a better way of doing it. There probably is, to be honest.
But it works.
If you scour the Metafor user guide, you'll probably find a really good way of doing it, which I haven't found. But that's a good question, yeah. So you can get, basically, it's how to get an array of different stuff that the studies have given you, to be in a compatible format. Yeah.
So eventually you just presumably need the study name, the study N, and the YI and VI, and then that's all you need.
Yeah.
Okay.
You basically only need
fine.
YI and VI when it comes down to it. Yeah.
Yes.
That's the only things that it will use. Yeah. So, going back to some theory, how are we doing for time? Yeah.
25 minutes.
Yeah, that's cool. Should be able to do the basics. So, there's this distinction in meta-analysis between running a fixed effects model and a random effects model. Have you guys heard of that before? No. Okay. So, you could probably spend a whole lecture talking about this. So it's really just going to be a basic understanding. The most common one to use is a random effects model. So this is these are models for looking at heterogeneity between studies. So where studies have different effect sizes, basically, what does that mean? You only use a fixed effects model when your sample of effect sizes from the studies you found are estimates, or you're assuming that they're estimates of the same underlying population effect size. So you're assuming that they are all estimates of one thing. However, that assumption is really easily broken, because if you imagine different studies using different methodology, slightly different participant groups, there's a million things that can change across studies that are looking at ostensibly the same thing. So most often you're going to use this thing called a random effects model, where your sample of effect sizes that you know about are actually probably estimates of different true effect sizes. Does that make sense? It will make sense if you've kind of got a background in statistics and like going from samples to populations. Yeah, okay. Yeah.
So the fixed effect sounds really, really limited. Have
Yes.
you actually got any examples of where you might actually use that?
It's a good question.
When the result is significant. that's when I've seen it used.
Yeah, some people will run both, and then pick the one they like. No, so don't do that.
Yeah.
Possibly if you know that all the studies you're looking at did like exactly the same thing. Do you think that's right?
If you was to do, say, an internal replication of your own study, or a replication that are tightly fixed together. The other definition of fixed, or the other way of putting it, is that you assume that the variation in the effects is just due to sampling error.
Yeah.
Okay.
So in everything else, if you expect the variation to be due to anything beyond that, you would use random effect.
Okay.
So you would just use random.
If you're unsure, use random effects.
Yeah.
So variation in methodology across studies means their statistics are most likely estimates of different underlying parameters. So the goal is to estimate the mean of the distribution of those effect sizes. And the command for that in Metafor is RMA, Random Effects Meta-analysis. So this between study variance, to talk about it a little bit more. suppose you conduct a random effects meta-analysis, you're allowing the statistics from each study to estimate a distribution of parameters rather than just one. And it's useful to get an indication of the amount of variability between studies, because eventually that's one of the key things, like advantages of doing meta-analysis, is then to be able to investigate that heterogeneity between studies, and have a look at why effect sizes might differ. So as Sam said, this between study variability in effect sizes can be either that due to just sampling variance, or kind of true differences in the parameters that you're estimating. And there's various ways of trying to pull those apart. So if you, Metafor has loads of functionality on this, that you, if you're just new to meta-analysis, you probably won't need or won't want to worry about. It has a good default that's been kind of tested and has favourable kind of, what's the word? Yeah, attributes. So if you do have specific needs, there's loads of different ones that you can use. What I'd just say is make sure you have a justified plan for using any of those rather than just trying out all of them and then seeing which one you like best. So probably just stick with this restrictive maximum likelihood, which is the default setting.
Was the default a reasonable justification for choosing it?
No, not in and of itself, but Wichtbauer has done a big simulation study, and you can cite that and say, I chose it because this guy recommended it. Do you want to add anything?
No, I mean, if you had the time, you could just run them all.
Yeah.
And see if it does vary. So you can say that your
you
results
can say
are not
you did a
based on the
scientific.
kind of, a component part of it, which would be the rigorous and exhaustive way to do it. But I think
it wouldn't actually take that long. All you'd need to do is change a tiny bit of your code and say the different estimators of between study heterogeneity didn't make much difference, or maybe they do, and then you might have to investigate it a bit more. But what these basically can do is give you a measure of how variable your effect sizes are, and you can use kind of various statistics to report that. So Hedges, these are two commonly used ones. So Hedges Q is the sum of the weighted deviations from the pooled effect size. So you've got like the mean effect size, and then you've got how far each study is from that. And you can do a significance test on that, which will tell you, like, have you got significant heterogeneity? And if you have a decent number of studies in your meta-analysis, you're very likely to find significant heterogeneity. And that's then a justification for investigating that heterogeneity by doing something like a meta-regression moderation analysis. It does have low power when the number of studies in your meta-analysis is very small. So you might not pick up heterogeneity that is there if you don't have many studies. And then I squared is the percent of variance not explained by sampling variance. And there's various kind of guides on the different ranges. So I'll show you more of an example in a minute. So all this to come to how to actually run your meta-analysis. You tell R to make a new object, which is the meta-analysis of your data. So your data is here, you're telling it where it is. You're telling it to run it on YI and VI, those columns that you've got in your data. And then this is the method that we just talked about. If you don't put that in at all, it will use Remel, which is the default. And then you want, so that's it running it, and then you want to tell it to show me what you found. So you just type in that object name and it will spit out something that looks like this. So to break this down, it's telling you it's run a random effects model. K is the number of studies, and tau squared means heterogeneity, and that's the estimator it used. You've got your I squared, which in this case was fairly high, 69.77%, so there's a lot of heterogeneity in the studies that went into that. And Q is high as well, it's really significant. So that tells us you might want to investigate that heterogeneity between studies and see what moderators of effect size might be associated with the variation. And it will also give you what you really want, which is your pooled effect size here. So that's estimate. And it gives you kind of the confidence intervals, lower bound and upper bound, p-value. Just a note, if you, like me, ran it on correlation coefficients transformed into Z values, you'll need to transform them back to R values before reporting them. So you can use this tiny command that I've written in down there. If you don't need that, then you don't need to worry about it. Any questions on the output? Okay, forest plots. Obviously really useful if you're running a meta-analysis, is to be able to visualise this heterogeneity and your pooled effect size. So the commands here are quite kind of complicated, not very complicated, but there's a lot going on. And the way that I learned to do this was by trial and error. So I'll take you through it a little bit. So forest, that's the command to produce a forest plot on the results of your meta-analysis, that's res. You can tell it to give your x-axis a label, so that will be something like the effect size, the scale that it's on. Actually, just to show you a forest plot for anyone who doesn't know. So you've got your studies down the side, you've got your basically each of these blocks, so the size of the blocks represents basically it's like sample size, but it's the weight that study had in the meta-analysis. And the bars here are like the variance. So the ones with wide bars tend to have smaller little squares in the middle. So this one down here, I don't know if you can see it, has a large square because it probably had a large sample size and it's got low variance associated with the effect size. And this one up here was probably a much smaller study. And at the bottom here you've got the pooled effect size, the diamond, and this is like the scale that it's on. So in order to have produced that, you had to tell it various things, what to label it at the bottom. These numbers are to do with the layout of the plot, and if you change them, you so for example, when I first put this in, the label up here was like off screen because the numbers were far too high. So I basically adjusted the numbers until it looked right. And there's probably much better ways of doing it, but that's how I did it. So yeah, adjust your numbers until it looks right, and you can label. So this study here refers to, I think it refers to this, I've actually called it a different name, but whatever you put in there will appear there. Whatever you put in here will appear up there. Okay. How are we doing for time? Yeah. Okay, so that's basically how to run a very bog standard meta-analysis. And how to produce a forest plot of it. There's a bunch of other functionality, loads in fact, that Metafor has, and I'm just going to whiz through some of it. Okay, so you can run a meta-regression to look at whether study characteristics are associated with the effect sizes that they have contributed. So this, you're basically running your meta-analysis again, maybe calling it something different, but you've added in a moderator. So in this case, I've looked at mean age. I haven't actually put in any output from this, I've realised, because I wasn't sure whether we'd get to it or not. But basically that will run your meta-analysis again and tell you whether mean age in each study is significantly associated with the effect size that study, or with the variation in effect sizes across studies. Does that make sense? Yeah. And you can do all sorts of fancy things like putting in multiple moderators. Yeah, there's like a world of possibility. Okay, this is probably more important. Testing for publication bias. You can do all of these in Metafor. So producing a funnel plot, doing the trim and fill procedure, failsafe N. So these are all ways of looking at potential publication bias. They don't tell you there is publication bias in this meta-analysis or not. You have to kind of interpret the plots and the statistics that it will spit out. So if I show you a funnel plot, do you guys want me to tell you about how to interpret a funnel plot? Yeah? So basically what a funnel plot is telling you is whether the effect size down the bottom is related to a function of sample size, let's say. So up here we've got like the studies with high sample sizes, and down here we've got the studies with low sample sizes. Now, because studies with small sample sizes that didn't give significant results are kind of an indication of publication bias is if those are missing from what you found in your systematic review. So if you've got this section where it's low effect size and low sample size, and there's nothing in it, that might be one indication that those studies haven't been published. Yeah. So if you have, so basically studies that have large sample sizes are more likely to get published whether they're significant or not. But with the smaller sample sizes, that's like the section that gets missed. So if you've got loads in here that have their small studies of large effect, and none in here, then that might be one indication that there's some kind of publication bias going on. It doesn't mean there is, it just means that you might want to investigate it a bit more. So there's some code here for producing that funnel plot. It's very simple, funnel plot of the results. You can also run a test of funnel plot asymmetry. So that will give you like, it's like a significance test. And you can also run what's called the trim and fill procedure. So basically what that does, is it kind of imputes the missing studies from this side to this side. So it almost like reflects these dots and adds them in. And it'll basically rerun your meta-analysis, but it's imputed those missing studies, so it'll give you a slightly different result. And then there's a thing called the fail-safe N, which tells you the number of studies or non-significant studies you'd need to have found or to add in order for your pooled effect size to become itself non-significant. Does that make sense? So, for example, in one that I ran, it gave me like 1,600 studies, non-significant studies, that would need to be added into the meta-analysis in order for my pooled result to then be non-significant itself. So that was, it kind of tells you that it's unlikely that unpublished studies will have that much of an effect, will have had that much of an effect. So the thing to note is just don't automatically like look at one thing and say there is publication bias or there isn't. You have to kind of put all the evidence together and discuss it if you're writing up. Yeah.
There's a bunch of different types of fail-safe ends.
Yes.
Because the problem with the Rosenthal one is that it's saying a zero effect. But you can, there are other tests, I forgot what they're called, that you can say what would be sort of minimal interest.
Yes. Yeah, so I don't know much about it myself, but I know that if you change the type here, then you can do all sorts of different ones.
You do have flexibility.
Yes, I believe so. Yeah.
And are they sort of using the trim and fill technique to estimate that effect? Does it say how many trim and fill?
Yeah, I think it's a different technique, but I'm not 100% sure. There's loads, like Sam said, there's loads of different techniques, so you'd need to kind of read up on which is the one that you want to use for what reason. Okay. It's 126. I think I've covered everything, like the basics. Just to whiz through, there's functionality for looking at testing for influential studies. So that's where it's like outliers, basically. There's functionality for doing subset analysis and sensitivity analysis. I'll share my slides and you can have that code. References.
We do have the room booked until 1:30.
Okay.
But it's strike day, so and there was no one here beforehand, so we could. Steve Williams is supposed to be giving a talk but I don't see anybody anywhere. So could I mean, I'd like to keep you hostage just a little while longer, but I don't know whether anybody else, because people have been like slowly sloping off because I guess they've got other engagements. But I don't know, maybe 10 minutes.
Yeah, that's fine by me.
Is that all right for everyone? Anybody want to go? No.
I need to go. Okay.
Yeah, it's fine. Yeah, I know how awkward it is. It's like a rush for the
Someone's birthday. I think at 1:30.
Oh, bring us some back. Yeah, sure. Thanks.
Much better.
One thing I wanted to ask, Izzy, is when you have studies with a within subjects design and a between subjects design, because with between subjects design, it's all down to how the effect size is calculated.
Yeah.
So I don't know.
I see.
So usually the convention is to calculate effects assuming a between participants design.
Yeah.
With the within participants design, you have to modify the effect size calculation.
Yeah. So to put an example on it, I'm just thinking. Are you thinking like, for example, if you were doing between groups, you could have a standardised mean difference, but you could also have a standardised mean difference to describe change over time within something.
Yeah, it could be like it could be something like that. Yeah.
Right. The short answer is I don't know.
Mm-hmm.
I'd imagine.
So I can tell you how I've done it.
Yeah.
So,
Great.
So, because the general idea is that let's staying with standardised mean difference. It's just one mean minus another over the average or pooled standard deviation. But it's assuming that the variance for the one mean and another mean is from a different sample.
Yeah.
But when you have a within participants design, I mean the strength and the reason why we do within is because some of the variance is shared.
Yeah.
So you can extract out that shared variance, and so you're left with variance which is probably due to the intervention or whatever the reason is behind the group difference. And there are different ways to do that. The easiest way is to sort of put in a sort of the correlation value of how correlated the variance is between the two means, right? But the fact is that nobody reports the correlation. So you end up having to just do so I've done it where I did a sensitivity analysis of different correlation values.
Yeah.
But there are other ways that it sort of almost, you can calculate, I forgot what it was called now, but there are ways in R to calculate that yourself. So it calculates something else, not the correlation value.
So it
sort of estimates
it.
Yeah, it's something, I think it's called RAD or something. It's a random something estimate, and that seems to be robust.
Okay.
So I'm labouring the point, but have you come across? I mean, does it mention in his guide or?
Not that I've come across. And I'm just thinking, like, I'm just trying to think. Are you? So you've got. Are you thinking putting information from a between studies design study with or within?
No, it's
or are you thinking like how to interpret the final effect size?
Yes,
that you come up with?
because if you do a division, right?
Yeah.
So if you have a mean difference of 2 and a standard deviation of 2, your effect size will be 1. But because if you have a within design and you have a difference of 2 and you take out that shared variance, then you have like a standard deviation of 1.
Yeah. Okay.
So you'll have a change in the effect size. So it would be sort of I don't know.
Adjusted.
Yeah, it would be greater for the within.
Yeah.
So if you do between, you are likely to miss an effect.
Yeah. Okay.
Which is a problem, and that's a particular issue if you find a null finding, because it just looks like you have done a bit of jiggery pokery and reduced the effect size artificially.
Right.
That's why it's such a. But nobody really talks about this, so you could just carry on and turn a blind eye to it. So to answer your point, it's more a case of how do you deal with the within participants' designs to make sure that you don't get this. Yeah.
I don't know of a particular function in Metafor, but there might well be one, because if you look at, I'll show you the thing. Don't know why it does this. You can just download. So this is all the functions that it has. Yeah. So, I mean, let's just go. I mean, you could search it for something. That's what I do, just search for stuff. Yeah, it's a good point though, and one that I never thought of.
I was investigating this a while ago because I was like, well, how do I compute edges G for within subjects? And the different R package solutions came up with different answers and made different assumptions. And I was like, oh, I'm terrified. I'm not going to do it.
Yeah, I mean, Michael Borenstein, he's like
meta-analysis.
he's an absolute gift of a person. He sort of recommends just putting in the correlation and just doing a sensitivity analysis, which I think is sort of.
I think that's.
It's sort of quick and dirty, but I think it does the job. You're being fair as long as you report everything.
On that subject, Borenstein guy, if you go to the meta-analysis website, there's I think it's him that's written that.
Yeah, there's a PDF floating around of.
It's really, I found it really helpful. It explains everything really nicely.
It's all in there.
Yeah, and it's
Just on that sensitivity analysis point, so do you then have to assume the same correlation for all the different studies?
Yeah.
So if there's heterogeneity between the studies in terms of the correlation, then you wouldn't capture that necessarily.
Yes. Yeah. So you would have to keep it fixed for all, otherwise it would be computationally. There is no. So in the recent meta-analysis I did, I just did 3 iterations of it and kept it fixed. So it was very. I didn't do it, thank God, but I have done it before. Does anybody else? Yeah.
Hi. Pretty new to meta-analysis, definitely new to meta-analysis. I've been trying to get my head around the fixed effects versus random effects thing. Am I right in understanding, as a preliminary question, that with the fixed effects model, you're basically assuming there is no heterogeneity?
You're assuming, assuming that all the heterogeneity that there is due to just sampling variance.
Right, so the very little initial stuff I've been looking into as I try to wrap my head around this, it sounds like there's a bit of a controversy about using random effects models, that they're kind of kicking them out of using them in economics.
Oh, okay.
Interesting.
And I wondered, is there a possibility that we're creating, by using random effects, we're creating a false impression of moderators that don't exist?
Right.
Yeah, it's a good point. I think it's all about how you interpret stuff. So you can run a fixed effects, you can run a random effects, and they might have different results. I think, and you can even report both if you want to, but what you need to do is kind of use your common sense or knowledge of the background knowledge that you have of the field, of everything, to kind of come to some reasonable interpretation of the numbers that it's spitting out. So I think kind of running one in isolation of any context isn't going to be helpful, but if you kind of have a reasonable justification for running either one, and as long as you don't kind of pull kind of sweeping conclusions from it, then I think, basically there's no right answer. I think there's obviously, with the fixed effects, you're introducing an assumption that might not be true. As you say, with random effects, in some situations perhaps you're investigating heterogeneity that's not really there. I think it would be very hard to tell for sure whether you're looking at a single population effect size or different population effect sizes. You can't really know that. So I guess it's just a question of using reasonable justifications for whichever thing that you choose, and then interpreting it in a nuanced way rather than just saying this is the case.
It's a very ideological area in my particular research field, whether things like educational attainment are dependent on gender or birth cohort, things like that. And there's one kind of vilified group which thinks that heritability is the genetic influence on these things stays the same throughout history in different conditions. And other people who say it changes with the wind. So it's the ideology that people would bring to the analysis would have a big effect on the choice.
Yeah, I'm sorry. And from my understanding, from my understanding, I think really the fixed effect model is actually one particular condition of the random effect model. Like suppose if you have one thing and then you run both of the model, I suppose it does actually have like a fixed sort of true value behind it. Therefore, even you run the random effect model, and then the standard deviation of the random effect model, which would be very narrow, because the thing is that there's a true value there. So therefore, no matter what, if you run the random effect model, if you see the standard deviation of the random effect model is huge, and then you can see there is some sort of things there. But if the standard deviation become very low, and then I think it doesn't really matter if you use the random or the fixed model. I would say. Yeah. So I personally prefer the random effect.
Yeah. I guess that's a kind of data-driven way of looking at it.
I think people like to use fixed because it constrains that kind of flexibility in how you analyse, because you